ก็อีนี่ใช่ไหมครับ I can do canoe. The answer is very simple. Oh yeah, I should leave it here. It will certainly not.
Oh, hello.
Hello, how are you? Good.
We recovered from yesterday.
celebrate อะไรเพราะว่าถ้าไม่บอกก็คงจะงงๆว่าแบบถูกไหมโอเคเนาะก็คิดว่านั่นแหละแล้วส่วนนี้ของพี่จอแล้วเสาเอามามา mix อะไรนิดนึงแต่ว่าตัดไอที่ contribute to physics อันนั้นออกนะเพราะว่ามันยาวไปอันนี้ก็ cover แล้วล่ะโอเคเนาะประมาณนี้
ใช้เวลาประมาณเวลาพูดนี่เวลาประมาณใช้เวลาประมาณ45 นาทีแล้วก็เป็นคำถามถ้าช่วง
ที่เคยมานี่พี่ใช่ไหม
ใช่เด็กเวิร์กช็อป
ใช่ใช่อิริกอะไรนะ
ยูนิคเวิร์กช็อป
เอาบอกก่อนจำได้ว่าเคยคุย
เวลาเดินเราก็อาจจะว่า
พี่เห็นไลฟ์อยู่
ที่เราบอกที่เชียงใหม่เสียมากเขาก็ตัดตัดต่อสารพัดบอกเสียมาก
จะเริ่ม exact เลยประมาณ5 นาทีเนาะจะได้ไปของ professor
เ คือถ้าแปลได้ก็แปลถ้าแปลไม่ได้ก็ลงภาษาไทยด้านไหนก็ได้พี่ไม่ตามเลยได้ใช่ไหม
โอเคเนาะได้เดี๋ยวให้พี่นั่งเสร็จก่อนพี่ไปนั่งเสร็จก่อนโอเค Good evening, everyone. We're gonna start the special event very soon. Dear colleagues, professors, students, ladies and gentlemen, on behalf of the Faculty of Science, Chulalongkorn University, it's a great pleasure and honor to welcome you guys to join this special event, which is held to celebrate 100 years of Chulalongkorn University. This event will also be in live YouTube. Today we have a special guest, Professor Gerard Hooft from Utrecht University in the Netherlands. He is giving a special lecture in this evening to us. Dr. Hooft is a professor in theoretical physics at Utrecht University. He shared the 1999 Nobel Prize in Physics with Professor Martinus Feldman for elucidating the quantum structure of electroweak interactions. He works on gauge theory, black hole physics, quantum gravity, and fundamental aspects of quantum mechanics. His lecture today, The Mystery of the Quantum Black Hole, will tell us about the interesting thing, fascinating thing, intriguing frontier. So, please join me to welcome Professor Gerard Hooft.
Okay. Thank you very much. Can you hear me if I speak like this? Okay, very good. Well, it is my great pleasure to be invited here to speak. I should also say it is a great honor to have been invited to be here to help you celebrate the 100th anniversary of the university here, and I'd like to congratulate all the members of this university with their anniversary. So the topic of my talk is some remarkable things that we are discovering about black holes. And the story goes way back 101 years ago. Rather precisely 101 years ago, there was a well-known astronomer, a young astronomer of his time, who had just learned about Einstein having discovered equations that explain the gravitational field in terms of fundamental physical principles. And he only equations that made sense in combination with his older theories of relativity. This became a generalization of his theory of relativity, therefore called general relativity. And Einstein discovered the equations for that, which are quite difficult equations. They are non-linear, which means that you can't simply add up two solutions to get a third solution. It's more complicated than that. Non-linear equations. And Einstein knew that non-linear equations are difficult, so he didn't write the exact solutions to those equations. That would be impossible. But he wrote some approximations. But this astronomer, Carl Schwarzschild, immediately after Einstein had made these equations known, he said, I can solve that in some special cases. If you have spherical symmetry, if you have a system which is completely symmetrical when you rotate it, then these equations become just manageable, and I know how to handle such equations. I am an astronomer, and as astronomers know how to do that. The planet Earth is nearly perfectly round. Most stars are nearly perfect spheres, and in those cases you can solve the equations of how the temperature and density and so on, how they are all functions of distance only. So he said, he sat down and solved the equations, and yes, he found a solution. Unfortunately, most for him, but also for the rest of science, he was already suffering from some infection that he had gathered, and he had only a few more months to live. So a few more months later he died, and he never learned how much commotion the solution that he constructed actually would yield. Because he said, well, this is just, just the ideal situation if you have all mass of an object concentrated to a point. So imagine that, so this is of course in German, but the English translation is underneath. The title of his publication was about the gravitational field of a point mass. So imagine all the mass concentrated on a point and calculate what Einstein's equations tell you about the gravitational field, and he found a solution, he thought. But he was a good astronomer, he was not such a terrifically good mathematician, because later mathematicians looked at that solution and said, wait a minute, it's not exactly the thing that he thinks it is. There's something very special going on with that solution. And they describe it as follows. Einstein's theory about gravitation is about the curvature of space and time. So space and time are no longer flat, but here you see what happens to space-time if you have some mass in the center, then it gets curved, it gets a shape that's different from flat space. A bit hard to imagine in a three-dimensional world, but if you have some fantasy, you can imagine how also a three-dimensional world can get curvature in it. And the mathematicians then said, yes, but that curvature that Schwarzschild wrote down is more complicated. It is more like having a hole in the center. And Schwarzschild didn't really understand that. He thought that hole is just a singularity, something, I don't know what it is, but that's where the mass of the object is sitting. Well, not quite true, because mathematicians could say, you don't need that mass. You can just have that hole in the center. But what does that hole mean? And the answer to that is that you have to imagine a second universe. So take two regions of a universe on top of each other, on top in a sort of imaginary dimension. Very difficult to imagine how it goes on, but imagine two worlds, and then this, what Schwarzschild wrote down was actually a hole that connects these two worlds. So actually, there are two universes, and there's something that connects these two universes in this way, which with some artistic freedom is indicated this way. But you can imagine that this is something like a wormhole. It connects somehow, in a funny way, these two universes together. The two universes don't have to be physically very close to each other. This brown region could be very, very far away, but you just fold it up in some imaginary sense without anybody noticing it, and bring these two universes close together, and then make a strange pipe-like connection between these two universes called a wormhole. And then, well, what does that mean physically? It's very mysterious. Can you go then from one universe to another universe by jumping into a black hole? Isn't that very dangerous? A black hole is a very strong gravitational field. Actually, the word black hole was not used by Schwarzschild, much attached to the solution much later. But now we call it a Schwarzschild black hole. A little bit contradictory, because that's not what Schwarzschild had in mind, but that's what came out of it when mathematicians are involved in the whole picture. So the reason why it's not actually a wormhole at all is that if someone wanted to travel from one universe to the other universe and take this very dangerous road inside, well, he would be killed by this point mass in a way which we can only explain mathematically in a more complicated fashion. But suppose the point mass wasn't there, then mathematicians would say he would go to this other universe. Well, not quite, because the boundary line between the two universes, this red circle, which is actually a sphere, it's called the horizon of the black hole. That horizon is a region of the black hole where time stands still. Time stands still. What does it mean? Well, it means that if someone travels to the other universe, from a distance he seems to slow down, actually after a while stands still. He doesn't move. He never gets through. According to someone who looks from the outside, he never gets through. However, according to the guy himself, if he makes a journey, he would think he would go through, and indeed he would think he would go to this other universe. Well, that's the mathematical way of saying things, but not quite physical. Physicists have some extra remarks to be made here. They say, well, this black hole was formed by some collapsing object. A collapsing star, when it becomes sufficiently dense, it makes a black hole. And the astronaut who goes into that black hole, following the matter of the star imploding, will be killed by the star. He won't be able to get it to the other side. But suppose you could idealize that solution, then there's something strange going on. But then, okay, physicists would say, well, no, sorry. His time would stand still. He wouldn't be able to get through. Not in our universe, not in our lifetime or in the lifetime of our grandchildren. He'll never get through to pass that red line. So no, you can't travel to another universe. But you can imagine that this situation causes lots of confusion. It's hard to talk about it here because there are many people around who are not really very well acquainted with these topics, so I can't go into the mathematical intricacies too much. But it's a very peculiar situation. And I wanted just to tell you what happened next. So, for instance, the guy who goes into the black hole will not go to the other universe, but rather he will be entering into the central part. There's this yellow star, which you now see in the center of the picture here, is a region. So this star here is what we call a singularity. That's where everything blows up. And this poor astronaut who thought he would be entering into this other universe would not enter there. He would be killed by that singularity. And that will be very much the end of that astronaut. Is that the end of the story? No, there's much more going on. But first I want to explain to you what an elementary particle physicist, why elementary particle physicists like me and myself are so much interested in this solution. And that's because particle physics as such is not finished. This here is my wife's favorite slide. She says, you must show this slide. It's so clarifying. It shows what I call the highway of physics, of particle physics. It's a highway, meaning that we are trying to advance further and further along this highway to the future, where we solve everything that's to be understood about the world. There are two kinds of signposts beside the highway. Here, there's a signpost which label the amount of energy you need to get there. Energy per particle. And today, where you see the words LHC, that is this gigantic big laboratory in Geneva, or near Geneva, where they collide particles against each other with as much force as possible. That thing can only generate energy to a particle in the domain of 1000 GeV, called a TeV. That's a measure of energy that you can give to any particle. And on the right-hand side of this highway, you see distances or sizes. Every time you increase a factor 1000 to the energy of a particle, you decrease by a factor 1000 the sizes of things that you can see. So these below the dotted line here, you see lots of symbols. These symbols indicate the kinds of particles that have been discovered in this domain. So there are light particles and heavy particles, and the heaviest particles have a mass that is close to this limiting line. And the last particle there is called the Higgs particle. That is the last thing that has been discovered experimentally. It was predicted theoretically long ago, but now it was also discovered experimentally, a very heavy particle. But if you want to discover even heavier particles or smaller particles, so strange here is that the smaller the particle is, the heavier it becomes, then you have to increase the energy by factors of 1000. If you want to see particles here, you have to increase the energy by a factor of 1,000,000. Well, we can't make this accelerator at CERN 1,000,000 times bigger than it is now. It wouldn't even fit on the planet anymore. So we have to find smarter ways to figure out what nature looks like. And what you see here is that all these particles are on this side of the dotted line. There's no particles there. Why are there no particles there? Some physicists think there are no particles there. But some critics say, of course there are no particles there. You haven't been able to see them because you couldn't make any machine that is sensitive enough to detect those particles or has enough power to detect those particles. So of course we see no particles there. They are there, but we don't see them. We don't know about them. This could be so, but whether or not it is so, we have our theories ready. So we have our theoretical machinery to describe particles in this domain. In principle, fully waiting for the particles to be discovered. Then we'll say, okay, such and such are the interactions, and we go on. Now, this machinery works well, but then there comes a problem in this domain. This domain, of course, a factor times 1,000,000 times 1,000,000 times 1,000,000, and then you're here. What is so interesting about that domain? Well, that's where the series stops. If you try to get particles smaller than that, something terrible happens, and that's the gravitational force starts to play a role. The gravitational force is extremely weak, but it intensifies faster than all the other forces if you go down this highway. And the reason why it intensifies is that gravity is sensitive to mass, and mass is proportional to energy. And energy increases here by factors of 1,000,000 times 1,000,000 times 1,000,000. So when you arrive at this point, the gravitational force becomes stronger than all the other forces. unfortunately, gravity curves space and time. So at this point, space and time are curved. What it really means is that this distance scales is so small that that distances, space is no longer flat, it is grainy, it has structure, it looks crazy, it becomes uncontrollable. Worst of all is we physicists don't really understand what space and time is doing there. Although some of us claim they understand it, but I'm not so sure they actually do, because you can surprise physicists if you say something that they haven't thought of before in this domain. So I claim that we haven't really understood how to describe things properly in this crazy domain. And that domain, by the way, is close to the region where grand unified theories, GUT, are constructed. This is where we believe that different forces of nature all become equal in strength. So something very special happens right here, but we don't know why that happens right there. And why not a little bit higher or why not a little bit lower? We haven't understood this point at all. We can theorize about it, but we would love to get more information. How do we get that information? Well, to get these problems straightened out, the problems that occur at this point. You see the words Planck length. Planck was Max Planck, who in 1900 discovered the quantization of light and at least the emission process of light. So Einstein later realized that light itself is quantized. That gave quantum mechanics. And Planck immediately realized that gave very fundamental laws, which in this domain must do something very, very strange. And I forgot to press the button. I should say that there are question marks here. We don't really understand what, in this Planckian domain, what the gravitational force does to particle physics. If you could clarify that, then we could be able to reason our way top down and figure out why things are the way they are. That's what we like to do very much in physics. Well, first of all, why is a Planck domain right at that spot? But that's the question that's easy to answer. We know that physics there will be controlled by three fundamental constants of nature. One is the fundamental constant that Max Planck discovered in 1900, called h, or rather we divide h by 2 pi, then we call it h bar, and that's the constant that is now controlling everything that happens with elementary particles, everything that's small. It's called quantum mechanics. Then we have here Newton's constant for gravity, and here we have the velocity of light. Those are three fundamental constants of nature which will all three become equally important in that Planckian domain. But you see all these things have dimension in terms of mass, of kilograms, meters, and seconds. So they all are different combinations of kilograms, meters, and seconds. But now I can take them in such a combination that I get the so-called Planck units. And that is, I take them in such combinations, either I get something with the dimension of length in terms of centimeters, or something with the dimension of mass, or something with the dimension of time. So mass, time, and size are no longer things that have fundamental dimensions that we can choose as our units of length and mass and time, but now they are God-given numbers. Assume that God introduced the constants of nature, then God gave us a fundamental unit of length and of time and of mass and of all other units in physics. The length scale is ridiculously tiny, even for particle physicists. 10 to the minus 33 centimeters is very, very small, even compared to the tiniest things that the LHC is detecting in its big accelerator. It's many, many orders of factors of 10 smaller than that. This mass is very interesting. It's the mass of a tiny grain of sugar or a somewhat large unicellular animal. It has a mass of 20 micrograms. And this time unit is the craziest of all. It's so tremendously small that no computer and nothing actually can measure such short amounts of time. So very crazy constants, but those are very fundamental constants where we believe that laws of nature take a completely new form. And what exactly that form is our task to figure out. How do we figure that out? Well, we know gravity is the problem. So one question one can ask is, where does gravity take where is gravity as strong as it ever can be anywhere? What's the spot where you have the strongest gravitational field? And the answer is you have to make a very tiny black hole. The tiniest possible black hole will have the strongest possible gravitational field at its surface. Nowhere will gravity be stronger than that. So what is the strongest possible black hole? The smallest possible black hole will be again 10 to the minus 33 centimeters. Smaller than that, Einstein's laws are no longer hold, so you can't talk about black holes anymore. 10 to the minus 33 centimeters is the smallest thing you can imagine, even for a black hole. How strong will the gravitational field be there? Well, as strong as it ever can be. If something special happens, it happens right there. So that's what we have to figure out. Study those tiny black holes. And then, when we figure out how things work there, then we will know how to study the fundamental laws of gravitational field when it is combined with quantum mechanics. Because this is, in a very simple phrases, the most difficult problem that physicists are encountering, to reconcile the Einstein's theory of gravity with the laws of quantum mechanics. The laws of quantum mechanics control everything that happens with fundamental particles, also atoms and molecules. They're all quantum mechanical animals. And they obey the laws of quantum mechanics, not the laws of everyday life, but the laws of quantum mechanics. Now, we want to have Einstein's theory also to be adapted to include quantum mechanics. We fail. At least I fail. Some people think they succeed in it. It's called string theory or superstring theory. But I don't understand those theories well enough to be able to trust those theories as describing everything I want to know about the Planck scale. To me, there's still too many mysteries there which are left not understood. Now, Einstein's theory has been described by many other people not in particle physics, but in general relativity. And one very famous person there is Stephen Hawking. He's in this picture together with Einstein and Newton. How can that be? How can you have a picture of Stephen Hawking together with Einstein and Newton? Well, Hawking was playing an episode in Star Trek. And Star Trek, there you can make time travel and so on. So at some moment he managed to put Einstein and Newton together, and they play a game of poker together with one of the characters of Star Trek. So the four of them play poker. And you can guess who won the game of the poker. That's a nice story of the Star Trek. Anyway, but Stephen Hawking was very famous in our field because he was the first to do a calculation where he investigated quantum effects in very strong gravitational fields. In particular, in the gravitational field of a black hole. And now, if you remember what I said in the beginning of a black hole, if someone travels into a black hole, somehow he takes an infinite amount of time to pass through the horizon. So when you have an astronaut who goes into that black hole, as seen from a distance, the astronaut will seem to stop. The astronaut will never go through the horizon. How it can be? Well, ask Einstein. It's a very complicated result of his equations that the guy stops. So even Schwarzschild had not quite understood it. So it's not easy to understand what it means that observer stops. In particular, the observer himself. The astronaut himself says, no, I'm not stopping. I'm going straight through. But the region he enters into is a region that's fundamentally invisible for anybody outside the black hole. And that's the infinite future. He ends into... For him, it's a finite amount of time that he needs to go to the infinite future. And that's the region behind the black hole. Well, the most important thing that Hawking stumbled into when he wanted to do some calculations was that these two observers treat the concepts of time very differently. Now, in particle physics, time is also a very central element of our study of elementary particles. If you know how to define time, you know how to define an elementary particle. If you don't know what time is, you don't know what an elementary particle is. Even particle physicists don't often realize this, but their definition of particles as opposed to antiparticles means that they have full control, they say, of the concept of time. But if you do something to the concept of time, you do something to the concept of elementary particles. And Hawking So Hawking started to ask himself a very basic question. He said, suppose this ingoing observer goes through the horizon as if nothing happens. He is not going to encounter very many particles. For all practical purposes, we can assume that this ingoing observer just goes in surrounded by empty space-time, because all particles there long ago have been swallowed up by the black hole. That observer peacefully goes into the black hole surrounded by vacuum, but he does go into the infinite future. Well, too bad for him, but at least we think, we understand, we can describe the world that that observer sees. And now we just apply Einstein and say, what will that world be looking like for the distant observer? And he stumbled into a difficulty. He tried to define what empty space is. Empty means no particles. So no particles for the guy who goes into the black hole. But what about the observer at the distance? He should also see no particles. Does he? There was a problem. The calculation made no sense. That observer seemed to hit upon particles. And that was because those two observers treat time differently, so they treat the concept of particles differently. If one observer says, I see no particles, the other says, no, I see lots of particles. So I'm not here in the right audience to explain in more deeper what this means. I would love to tell you more about the mathematics, what this has to do with creation and annihilation of particles and with Fourier transformation in time and all that. But I leave that only for the physics expert. They understand what I'm trying to say, that if you treat time differently, you treat particles differently. So this outside observer, this astronaut who stays at a safe distance from the black hole, will see particles coming out of the black hole. So there's this strange disagreement, and Hawking for a long time, no, not a long time, for some time thought he was making a mistake. He said, I don't understand what this is. But then he had the brilliant idea, a genius idea, to say, let's calculate how many particles actually there are. And he found that the black hole just glows like a light bulb. It emits particles just like Max Planck calculated how many photons are emitted by a heated object. He found that a black hole has a temperature. And with that temperature, it emits like a light bulb. And that you can calculate. You can calculate how many photons come from a light bulb. That same calculation applies to a black hole. You can calculate how many particles come out. It's all finite, all meaningful. Why not? So he said, well, I calculated black holes emit particles. And so, and there the lowest formula, I won't bother you too much with formulas, but this formula tells you what the temperature is, and just a number that you can calculate. For a black hole as heavy as the sun, such a black hole is about 3 kilometers in size. Well, the sun is much bigger, therefore the sun is not the black hole. But if you would concentrate all the mass of the black hole of the sun into a black hole, then it would be 3 kilometers in size. And such a black hole would have a temperature of 10 to the minus 8 Kelvin. That's very, very low. So nobody would see a thing. That black hole would be really black. This is a very low temperature indeed. That only with much, much difficulty would be possible to produce in a laboratory anywhere. But for smaller black holes, if the lighter the black hole is compared to the sun, the higher the temperature. If the black hole is very, very light, the temperature is quite considerable. So this was the outcome of his calculation. What does it mean? Well, think of a black hole and think that you're throwing things into the black hole. You can throw things of all kinds. You get into the black hole, but then the black hole will emit particles as well. This is what Hawking discovered. A black hole emits particles. And that's beautiful, that's interesting. That makes a black hole look like other objects that emit particles. Except for one thing. If the black hole emits particles, it must lose mass because it loses energy. So it also loses mass. It becomes lighter. When the black hole becomes lighter, it emits more particles. So the emission of radiation becomes more intense. In spite of the thing becoming smaller, its surface area becomes smaller, but when a temperature heats up, the intensity of the radiation becomes the 4th power of the temperature. So the lighter the black hole is, the more radiation it actually emits. So now you can ask the question, what happens if this goes on for a while? What happens with that kind of particle emission? Well, the whole thing will explode. And that will be a gigantic explosion. That will be an explosion that you will be able to detect from many light years difference. So when Hawking made this, he of course discovered quickly enough that the black hole will explode because of Hawking radiation. And that explosion, he could calculate easily the intensity would be enormous. So he said, well, let's ask astronomers, do you see flashes of light every now and then in the universe? Astronomers said, yes, we see flashes of lights. They're called gamma ray bursts. And so Hawking was very excited. Gamma ray bursts, maybe that's black holes. But then quickly astronomers said, no, they're not black holes, because every single gamma ray burst is associated with a galaxy. There's always a galaxy there. So it's in centers of galaxies. They do have something to do with black holes, with very big black holes, not the tiny ones. And they also can give gigantic flashes of gamma radiation when they are being formed. So that was a true answer. So we are still waiting to see a black hole decay according to Hawking's formula. It would be fantastic if anybody could observe such a decay. But anyway, it was just discovered that black holes now look a little bit more like ordinary forms of matter, because you can put things in and things can come out. If you have a bucket of water, you can put more water in, but you can put it in a refrigerator, or you can put it just in outer space. It will also evaporate. So water molecules can go in, water molecules can go out. And all that according to laws of physics. And now we find that black holes obey such laws of physics. So a question was, what's the difference between a black hole and ordinary particle of physics? Does a black hole not perhaps look like a particle of physics? Or conversely, could we associate every particle in the physical world with a black hole again? Is that possible? Well, it looks a little bit like it. We like to think of particles in terms of Feynman diagrams. And this diagram here indicates that particles which make a black hole, they come together like a star collapsing. It explodes to make but then it also implodes to make a black hole. And that black hole then can then again radiate particles, and particles come out again. So this looks like a nice time reversal symmetric picture of black holes. This is the way we would like to see things. And actually, the picture became more and more interesting, because if you assume this, that this picture is actually time reversal symmetric, then there's one thing you can calculate. And again, the statement I'll make now will only be appreciated by particle physicists. They know something about phase space. Phase space is how many possible things can a thing decay into. And the larger phase space is, the faster the decay of an object. Well, we know the decay of the black hole in the direction to the right, and we know the decay of the black hole when you time invert that. So the two processes can be computed. And so this way you get some information about phase space of a black hole. We did not have that information before, but we have it now. And the answer of that is astounding. And in fact, extremely intriguing, saying that black holes must have something to do with elementary particles. A black hole has phase space. What it really means is how many quantum states can a black hole be in? And this was an elementary calculation that we could all do on a back of an envelope, relatively simple. And the answer was that the black hole behaves a little bit like this. It behaves like a sphere with fundamental squares on it. Every square is the Planck length square, and these squares are blinking on and off. It looks as if the black hole is a dynamical object doing this kind of thing. But besides that, there are again a few of these bits on the side. They are what every black hole has in common. Every black hole has the same number of bits here, and then the others depend on how big the black hole is. Massive black holes are much bigger than tiny black holes, so they contain more of these elementary squares, so they can be in more quantum states. But this looks very much like a theory of particles. Look a little bit like the theory of an atomic nucleus, which can be in many quantum states, or elementary particles even can be in several quantum states. In string theory, strings can also be in quantum states. So this looks like we nearly got to the point that we want to understand things, that black holes are objects with an interesting internal structure. So this comes, by the way, from the picture that you can invert the whole theory of Hawking radiation. You can think of Hawking particles going in, and then maybe things can come out this way. This is sometimes called a white hole, but the claim now is that the physics of the white hole should be the same laws of physics as a physics for the black hole. That's what it said here. So white holes and black holes should be the same thing. This is a great, nice starting point. So we should be able to use that to compute all the properties that the black hole can have. So now we can find out how the quantum states of the black hole evolve in time and so on. Let's sit down and compute this. And this should then be the first step to solve everything, to solve how quantum gravity behaves at the Planck scale. Because these little squares are Planck in size. So we're really doing Planck physics now. So let's go on with it and do this computation. And then you discover that there's something very fundamentally wrong. It doesn't work. And here, theoretical physicists for a long time were at a loss. We didn't understand how to proceed. How do these blinking squares actually blink? What are the rules? How do they emit particles? How do they absorb some particles? I would like to see those equations, just like we have all the other equations in place. But these equations we don't have in place. So something is very, very fundamentally wrong. What was wrong? Well, if a black hole is like a blinking object, it would mean that if you throw something in, then that determines what comes out. The behavior of a bucket of water, as soon as I add some molecules of water, the bucket of water will evaporate differently from what it did before. And according to the rules of quantum mechanics, this is very important that if you start with two different objects in the beginning, they'll behave differently at the end. There's no way you can avoid that. You can never have something become the same as something else if it starts out differently. That's the rule of quantum mechanics, a very fundamental rule of quantum mechanics called unitarity. It has to be like this, otherwise we can't write the equations. A black hole didn't seem to obey unitarity. Different black holes from the beginning end up being exactly the same. If you throw something into a black hole, no trace is left behind. At least not according to Hawking, not according to Einstein. If he had lived to calculate this, he would have agreed. You can throw different things into the black hole. After a while, they will look exactly the same. You won't see the difference anymore. How can that be? So this was a difficulty called the black hole information paradox. It has to do with information. By looking at the black hole, can we reconstruct how it came into being? The answer is no, you cannot. Not according to the laws of nature that you know today. So this was a difficulty that we are encountering. And difficulty is fundamental. It's called the black hole paradox. Now, there are different possibilities to resolve this paradox. And here, people took different sides. There was the Hawking camp, which actually could include most of all the people who did general relativity, but hadn't spent much time yet in particle physics. So they were specialists in general relativity. And those said, well, too bad. The black hole doesn't obey quantum mechanics at all. But if that is so, the Hawking particles themselves violate the laws of quantum mechanics. And that is very strange, because we use quantum mechanics to derive their properties. How can you have that a system, you use a theory to derive the properties of a system, and then you find the system disobeys the theory? It can't be right. So something very, very problematic here. This cannot be correct. So, as a consequence, you had the other camp, the camp of people who had their education in elementary particle physics. They said, no, this can never happen. Black hole information somehow must come back to us. How exactly, we have to figure out. It's our job. We sit down and do it. And this caused big discussions over and over. And it was Leonard Susskind who wrote a book about this. He called it the Black Hole War between the particle physicists on one hand and Hawking and other people in general relativity on the other. What happens to a black hole, to information that was thrown into a black hole? He calls it the Black Hole War, and he thinks he's on the winning side of that war. I was with him in that respect. I also started doing particle physics, and then seeing what black holes do, and say, no, that information must come back to us somehow. Black holes must obey unitarity. But there were alternative theories. Originally, people like Stephen Hawking said, no, the There's loss of quantum coherence in the black hole, and therefore the information disappears, and if that violates quantum mechanics as such, too bad, but that's the way it is. After a while, there was other options were coming along, and one option was the black hole somehow emits its information back again. It's hidden in the Hawking radiation, but not quite. It could also be hidden in what's called the black hole remnant. So the black holes don't decay completely, they decay until they become a very small hard object, which still contains all the information. This would disobey all the laws of physics that we've learned in particle physics. So we didn't believe this thing either. Then there's the option that the information comes back, but only in the very, very end. It's hidden in the Hawking particles, but only very, very late after the evolution of a black hole. And finally, the fourth option was no, the hidden information comes out immediately. As soon as you throw something into the black hole, it does affect the Hawking particles coming out. And well, the way I see it at least, Hawking started here, but after some time in the early 2000s, his view changed here, then his view came here, and this is where Saskia and I have been sitting all along, and I think we're coming closer together. We'll see how it works. How can it be that this information that got lost can return back to us? And here is a question of interaction. So here's a horizon of black hole, here's an incoming particle, here's an outgoing particle. And the outgoing particle should behave in a way that does not depend on what the ingoing particle does. Well, unless to interact. So maybe at that spot here, there's an interaction taking place. Could it be that because the ingoing particle interacts with the outgoing particles, that interaction leaves a footprint behind in the outgoing particles? Well, this is where most people said, no, that cannot be because the interactions between particles are very weak. So the interactions are far too weak for ingoing particles to pass on all its information on the outgoing particle. But wait a minute, not all interactions are very weak there. The gravitational force becomes very, very strong, because the closer you are to the horizon, the smaller the distance you're looking at, the stronger the gravitational force becomes. It becomes by far the most dominating force. So maybe gravity does the trick. Does it? I claim it does. And the way to see it is this way. If you look at the horizon of a black hole, but now through a microscope, so you don't see the curvature anymore, but you do see all these Hawking particles queuing here, waiting to go out. They take a very long time to get out. So only the ones on top go out first. Those go out much later. There's an infinity of Hawking particles right on this line, which takes ages and ages to get out. But now if I throw a single particle in, it does the following thing. It has a gravitational force. The gravitational force does this. It drags those particles along. So many of those particles actually are dragged into the horizon. That's a big change, because eventually these particles come out and they carry that information along in a very vivid way. So the claim is the information doesn't get lost at all. The gravitational force ensures that any ingoing particle leaves its footprint in the outgoing particles. This is again a picture, I'm not sure you'll immediately grasp what it is. This is these two regions. And this was the point where time was standing still. This is the other region, but now seen through a magnifying glass. So here in this region, things can go into the black hole, and this is the horizon. You have to go faster than the speed of light to stay out of the horizon. Once you're here, you're lost. You're going vertically into this region of the horizon. So this is one universe, this was the other universe, and a Hawking particle then goes like this. A Hawking particle comes out by some strange vacuum fluctuations, which Hawking for the first time understood. And these particles here come out, and they come out as real visible particles here. But now I send in something in, and people thought that it left no trace. But it does leave a trace, because it drags the other particles along. So this particle which wanted to come out now is dragged in again. And when we did calculations, we said, so there's a problem, because it's dragged in, but now becomes invisible. So how can this affect? How can this leave a footprint? And then a year or so ago, I did another calculation on this, and I made a mistake. The mistake was that the particle, I let the particle come out like this. Instead of going out here, it went out like here. And I said, I solved the problem because it's beautiful. Because the indigo, if it doesn't come out in this domain, it comes out in that domain. And then you're done. Because now the information can come out of the black hole again. But actually it looks a little bit more like this, that a particle going in, either it leaves some information going out here, but it can also leave information going out here. So the information doesn't get lost anymore. It comes out in this domain. There's one problem with that, and that is that it comes out with momentum, depending on in a position that depends on the momentum of this particle. The more the momentum of this particle, or the energy of this particle is, the further this one is dragged along. But now those who know what quantum mechanics know that there's an uncertainty relation between momentum and position. So if you know the momentum of this particle very precisely, you don't know the position of this particle very precisely. Actually, you don't know whether it comes out in this region or whether it comes out in this region, and then I have to let it go in that direction. So there's an uncertainty whether a particle comes out in region 1 or region 2. And this means that these two regions actually talk to each other. So this is a picture. If my ingoing particle has a very sharp wave function, the outgoing particle has what we call the Fourier transform of that wave function. It's spread out. It can come out in region 1 and in region 2. And this gives a problem. And the problem is very severe. And if the situation would be like Hawking originally imagined, that this black hole is a wormhole between one universe and another universe, this would be a way for the two universes to talk to each other. That's fine if you're like Hawking, you love science fiction, but it's terrible if you love to have orderly physical laws, because now if these two universes talk to each other, it means that they are sending information of a kind that makes the local laws unpredictable. So it makes all laws of nature unpredictable. If there are tiny black holes, I want things to be properly, orderly described by equations. So this can't be. There's something else that you have to do. And so Hawking would have liked it, the idea that two black holes talk to each other, but there's another answer. And I find the answer is much more rational. And that answer is that actually the region 2 that I described is not another region at all. It's just the other sides of the same black hole. And this is an option that has been thought of earlier. I'm not the first to say that. I mean, there are other people who also had this idea that perhaps the two opposite sides of the black holes are linked by this wormhole in some way or other. But now we see it's absolutely essential to assume that. Otherwise, it doesn't work. So remember that we had this wormhole connecting two universes. We thought it was universe 1 connected to universe 2. Now we say, no, it's not universe 2. It's just the other side of the same black hole. I have to watch my time. And so what came out of this, and I'll just very briefly make a few more remarks, and then I hope to get some opportunity for questions. What came out of this is the black hole looks like a region of space that is such that if you enter in one spot, I enter here, and there, I immediately emerge at the other spot. So, yes, you can see it there. So the wormhole connects this point to that point of the black hole. That means there's nothing inside. There is no inside of a black hole. All this is fine, but what it does, it changes what we call topology of space-time. If these situations are allowed in our physical laws, we have to rewrite the laws of physics at the Planck scale. This is exactly what we want gravity to tell us, how to rewrite the laws at the Planck scale. We haven't understood the situation, so this is a complete mystery. How can it be that you have this little sphere excavated out of space-time, such that if you enter here, you're not wasting any time inside, you immediately re-emerge here. And well, you re-emerge beyond time equals plus infinity, so that's ridiculous, but you can also re-emerge at finite times, and then you're Fourier transformed. Momentum and position are interchanged. Very crazy way of re-emerging. It's not advised if you want to travel that way, because you are being blown to pieces. But the laws of physics stay in one piece, and that's all that counts. So this makes our theory very interesting. So I think what it really means, is finally summarized here. I would love to have some sort of discussion in this room. So if people want to ask questions, the more critical or nasty the questions are, the better they are. And I also define by now there are no stupid questions, so anybody can ask questions and interfere with what I wanted to say. There you can read about this in a much more technical manner in these two papers, but they are only for the expert physicists. They're not really intended for the public. They'll be very difficult to read, but there you can read all the technical details that go with this story. I try to leave out all the equations, but there, if you want equations, you can get them in right there. And so this is the end of my talk. I would love to have reactions of any sort. Thank you very much.
Thank you very much for your wonderful talk. So now we wish to have audience to ask questions and discussion. Before we begin the session, I invite Dr. Pavin. So just in case, because he's in this field, to be the acting moderator with me. Okay, so what is your question?
Thank you, sir. My name is Pushin Hongsawat. I'm come from Mahidol University. So my question is, lately I have read some of scientific of physicists who he mentioned about that there is no gravity at all, and he studied about quantum and thermodynamic. He mentioned that it was a result of thermodynamic or a quantum. So what do you think is that?
I'm not sure, but maybe that physicist was our former student Erik Verlinde, because he exactly said that. Maybe not exactly those words, but he said that he could understand gravity as a consequence of information content in nature. And he said that in models of statistical physics, sometimes if a state is more probable than another state, the system is driven in that direction. So statistical distributions of particles sometimes generate forces or things that look like forces. And his theory is that gravity is a force of that nature, that there is some hidden information in what we call vacuum space that actually causes things effectively to move in certain directions because those directions are more probable than others. And I'm not really in the right position to criticize that, but I think that that I haven't seen quite the kind of equations that I would like to see in such a theory. So I think that the route I've explained in my talk now is a more direct route to try to understand what happens at the Planck scale. But I do sympathize with his ideas that there could be some statistical underpinning of gravity, not only the curvature of space-time, but also the existence of information in space and time. Information is a very central issue in all our understanding of gravity.
Thank you, sir. And I have another question. It would be, what should I study next if I choose in the major of physics? Which way, maybe in a gravitational or quantum? Because it seems like that if there is no gravity, so maybe quantum is the best or something.
No. As you feel with your feet right now, gravity exists in the sense that there is something that behaves in all respects like a force pulling you down in the direction of the center of the Earth. There's no denying of that. The thing you can deny is what kind of words should I use to describe this effect that I'm being pulled to towards the center of the Earth? You as much as I do. So, and Einstein then said that this should be independent of the velocity of the observer, and the laws should be such that they obey the principles of relativity. Then you get general relativity, and general relativity has been tested with high accuracy, so at least a lot about that theory is correct. So but the only thing is, we want to ask further questions. Are there underpinning theories of general relativity? And that's the kind of questions that Verlinde is asking. Are there theories underneath both quantum mechanics and gravitational force that should put everything in one basket, so to speak? Probably we need a different wording, but the problem is still the same. The problem is we have gravity as a force. It acts between particles. How can we reconcile that with quantum mechanics and with theories about information? Most of us agree that even empty space does contain information in a way that's hidden from us. How can we incorporate such ideas into understanding gravity? And that's a very interesting way of posing the problem. It's not my own way of posing the problem, but it is a way to posing the problem, and you might be able to contribute to that. So it's not. So I would not advise you against studying those theories. You do have to realize, however, that we're very far away from applied physics, right? We want to understand how to apply laws of physics in order to make better machines, better refrigerators, better energy generators or whatever. And that's not the way to go to ask such questions in gravity. However, these questions do play a very fundamental role in our understanding of the world that we live in. If that's what you're interested in, then I should advise you strongly to proceed with this kind of study, including gravity.
Thank you for the answering, sir.
Oh, it also works.
Hello, my name is Nathanon. I'm a high school student. Yes. Can you hear me?
Yes.
Okay. I'm sorry. It's my real pleasure to talk to you, sir. And I have a question. My question isn't about the quantum, but it's about discovering of new particle. And my question is, to discover a new fancy tiny particle, you need a collision with high energy, and that is exactly what we do with the Large Hadron Collider. And to make particle reach its energy, to make particle have high energy, you accelerate them in the particle accelerator. And they have a limit, because no particle in this universe can go fast enough to the speed of light. And the question is, if we can make any particle faster than light, how can we achieve more energy?
Well, according to all present wisdom, you cannot make particles move faster than light. But I say all present wisdom because there are many people who speculate that perhaps particles do exist to go faster than light, or perhaps something can go faster than light. But if you want to do that, you will have to make a big mess in Einstein's theory of special relativity. The kind of mess that we particle physicists and most other physicists are not prepared to do. To throw such a beautiful theory in the dustbin altogether is not the right way to go. So we say the situation is more complicated. You have a problem in your hands then about causality, the order between cause and effect of phenomena in nature. And the whole theory of analytic particles we have so far is a consequence of us systematically distinguishing order and the order of cause and effect. Because if you throw that through the window, you cannot make a standard model of analytic particles anymore. And that model has been extremely successful. So I would say no, it's not the right way to go to just think of particles going faster than light and making a mess of Einstein's theory of special relativity. That's probably not right. So we have to be smarter than that. In our minds, we can make particles have any energy we like. So nothing stops us from fantasizing those particles and moving the Planck energies or whatever. But to do experiments is very hard. So what you have to do is be very smart theoreticians and see if you can make some predictions about particles that you couldn't make otherwise. For instance, the standard model contains still very many mysteries that we don't understand. If we can unfold all these mysteries to be something that we can compute, like many of the coupling strengths of particles cannot be computed in basic physics today, we have to get out experiments. Maybe our new theories will give you relations between those numbers, or if you can give those numbers themselves, and that would be a calculation that you can then check by experiments. So it's not impossible to check the steeds by experiments, but experiments will have become more and more indirect. And there's a problem with indirect experiments, which is their interpretation. You can interpret the outcome in many, many different ways. So we have to be very sure that we interpret those experiments correctly. But in principle, that is the way to go.
So mathematics is the best way to make discovery of the particle.
I personally am in favor of trying to do mathematics as accurately as we can, and don't run into wild speculations like now. Because most of my friends, because they can't solve and they have not enough imagination to apply rigorous mathematics, they imagine something isn't there, and they make toy models that do not describe the real world, and then calculate those models. And that's very interesting, but often doesn't give us the answer we want. So I'm in favor of doing the kind of things that I've explained about here. Apply laws of nature as you know them, but try to see where they clash. And yes, the laws that you know today, they do clash in some spots. And now you have to use your imagination to be very, very careful in throwing away things that have worked in the past. So don't do that as much as you can. But try to see if you can be smarter than today's textbooks on physics. And sometimes that's possible.
Thank you, sir.
Okay, we have okay, just after that.
The mass, the Planck mass seems to be of a much larger scale than the time and length quantities. Is that mass, the amount of mass required to create a black hole having a diameter of the Planck radius?
Yeah, the Planck scale, so the Planck length, the Planck time, the Planck mass are such that everything becomes of order 1, so to speak. So if you take a Planck, if you take a black hole with the size of the Planck length, it gets the mass about the Planck mass, and its fluctuations will fluctuate in a time that's about the Planck time. So all these things come together. So the heaviest particles will probably also be particles with the Planck mass or something like that. And again, their frequencies and their masses and their sizes will all be in the Planck domain. Because that's the domain, you know, all these constants, Newton's constant, cosmic light, and Planck's constant, they're all one by definition. So they're all equally important. That's what defines that scale.
Okay, clock. Sorry.
Okay.
Okay, I want to ask about the thought that you speak about the region 1, 2, 3, and 4 is the cone of light. I want to know why did you say that? If I want to know how is it possible that if one particle travels into the region 1 and it can reappear in region 2 or something like that, because from which I understand, I think that, can you please, I want to go back to that slide.
Sorry,
I want to see that.
I'm not sure I understood the question. I've just this country region 1 and region 2 are the regions that well, the wormhole connects region 1 and region 2. This is the wormhole, so to speak, but it involves regions 3 and region 4, which sometimes the other way around. Anyway, it includes these other two regions, but this is the infinite future, and that's the infinite past. But I haven't quite understood the question.
Okay.
Can you repeat the question just very briefly?
Okay, I want to know the difference between the region 1, 2, and the 3, 4, which is in the cone of light.
Yes.
And I want to know how it is possible that the matter going in can reappear into the region 2 that you speak of it.
Okay, so here, so the calculation, if you just use the physics books, the calculation would give that a particle coming out of some fluctuations out of this forbidden region 3, it would be dragged like that and it would also come out in the forbidden region 4. So that particle would stay invisible. So it's not really useful as to describe the state the black hole is in, because this is invisible and that's invisible. But then the idea is, if you do it this way, then and then you can say that this particle was visible when it came in. It runs into the invisible space, doing no good anymore because nobody can observe it. But yes, we can observe this. If we now say this is the other side of the black hole, then this particle comes back this way. But this is not the particle itself, it's the information carried by the particle. So that's the particles going in that direction, but they now carry the information of the ingoing guys. This way the information gets conserved, but you need the two regions of the black hole. You can't have it all happen in one region. And that was in the old theories, everything happened on this side. No, you also have things happen at that side. And you see how particles can communicate from one to the other. So you have to apply them both. So now the idea is this could be another universe, but then I have physical effects going from one universe directly to the other, and that can't be right. That's not a local law of nature. But if this is just the other side of the black hole, then everything seems to come together rather peacefully in a set of laws of physics that I could understand. That was my criterion.
So is it just its information, not the particle itself?
Yeah. So this is information rather than a particle itself, because it came from vacuum fluctuations that sit way out here. So it's you can also say the particle is being scrambled. This particle is being tremendously scrambled. It comes out here, but in a way it's hardly recognizable, but sufficient for the laws of physics now to work. And that was what I was after.
Okay, thank you.
Thank you, Professor. I have another question about this process. So do I understand correctly, please correct me if I'm wrong, if when you identify these two regions by connecting the antipodes of the black hole, is there also a connection between the infinite future of region 1 with the infinite past of region 2?
Not so directly, because I'm asking the question of a physical law that tells you how things evolve. And this law tells you how this sits in the physical space and it evolves to something else sitting in the physical space. So that then works. Now this is the infinite past, this is the infinite future. And I'm not interested in describing what happens beyond the infinite future. I would say that's not physics. That is mathematically very interesting, maybe philosophically interesting, but physically I can't do anything with that. So I won't say that this is directly related to that. I mean, you could say that, well, there's a particle from a vector fluctuation coming here, and then it re-emerges here. So maybe that's a connection between these two regions. But I don't need that to understand how the laws of evolution go. For those laws, I only need the white spaces here.
Thank you. Sorry. So I'm just concerned if is there any way to treat then the problem that an infinite past could not exist in our universe that we think is not infinitely old? Or does it affect the explanation, or it doesn't matter?
Okay, the thing missing in this picture is whatever made the black hole. Most black holes have in their past a collapsing star, or something which was not a black hole, but collapsed due to gravitational collapse. That collapsing matter still sits here. It sits, in fact, it comes here. Here comes that collapsing matter. Along that, very long ago on the horizon, it just sits here. And the collapsing matter has so much energy and mass that it causes tremendous curvature of space-time, which says this solution is actually incorrect. This wasn't the past of the black hole. The black hole had a regular past. This is an imploding matter. But that makes the picture much more complicated to do mathematically. So for a moment I say, well, I'm not interested in the infinite past of the particle. I know the thing has likely been formed by a collapsing star, but I'm not interested in what the collapsing star is because it's too far ago, too far in the past. I only want to know how the thing behaves in the present, and then it's very useful to leave the imploding matter out for a while. And that makes sense, as it turns out to be, when you later work out the equation, say, okay, it makes perfect sense to leave that out for a moment. We can put it in later if you want. to see that actually how the black hole started does depend also on how the collapsing star actually collapsed. So that information I threw out, maybe that was incorrect, but for the time being, it's the best way to describe the evolution. Like when you have an atom, you can ask, how did the atom ever form? What was its past a million years ago? It's a very interesting question, but not relevant for the behavior of the atom right now. So the same thing is not relevant for the behavior of the black hole now. What happened when it collapsed ages ago? But that information is, of course, implicitly hidden in it.
Thank you very much.
เดี๋ยวเรามีเวลาสำหรับสัก 1-2 คำถามนะครับ
I'm curious about the information on the surface of black hole. What is actually a bit in the surface of black hole, and how is it related with like what you said earlier about the problem of information?
Again, I'm not quite sure I understand the question. Let me go back to.
Like, what is this bit actually is, and like what's observable can we distinguish between each different quantum bit in the surface of black hole?
In the very end, the belief is that these blinking squares roughly represent in and outgoing particles. So every little square here blinks when a particle goes in, and it blinks when a particle comes out. It has something to do with that. Exactly how, we don't know. I mean, we don't really know how to characterize the information on this. I mean, mathematicians know how to do many, many transformations. So to say, if you have one set of blinking lights, I always perform a transformation and get another set of blinking lights. So my question will be then, how to get the best possible representation of what happens here so that I can make sense of how the black hole reacts when the thing goes in and the thing comes out. So just like in a hydrogen atom, and that was also some element of the calculation which I left out now because it's more for the experts, but you can treat this thing very much like a gigantic big hydrogen atom by saying that the hydrogen atom became easy mathematically to handle because we can expand the electrons going around the atom in spherical waves. You can do the same thing here. You can expand this in terms of some spherical wave expansion. And these spherical waves that obey much simpler equations, and you can then ask how can I represent those equations most efficiently as possible. That's a mathematical exercise. But you can imagine it doesn't really matter what kind of basis you use, what kind of formalism you use, as long as you can predict as best as you can how the black hole will react when things fall in or things coming out. So that is the basic question. And it's hard to say that anything specific happened here as long as you don't know really what you're talking about, because we still don't know exactly how to characterize this thing properly. As long as we don't, it's very hard to answer questions like what I think you're asking, which is, what is it that's blinking here?
Okay, thank you.
ขอคำถามสุดท้ายนะครับ
Hi, I would like to ask your opinion about. So you said there are 4 ideas which you and Hawking think about this issue, right? So there's those 3 ideas that Hawking changed his mind over time. So I just want to know your opinion about his last his previous standpoint that he said maybe the information that black hole leaks. I mean, so can you change the slide to that one? Sorry, the one that you call 3A.
Let me see now.
Yes. So I just like to ask your opinion of what is the weak point in that 3A approach that makes you think maybe it's not the right way to think about it.
In 3A, the black hole is assumed to have a very long-lasting memory, so that the information that you put in now only comes back much, much later. But what I think I could show is that the information doesn't come out much later. It comes out later, but in a relatively short time span. The amount of time light takes to go across a black hole is a short amount of time. You have to multiply that with a logarithm, the logarithm of the size of the black hole, so that it might bounce many times, but not more than 10 or 20 times or so, and then it will come out. So that's a time scale, which is actually a very short time scale. So that's why I say I favor 0.4, where that small time scale is sufficient for the ingoing matter to have an effect on the outgoing matter.
Right.
So you have a particle going in. If the black hole is like the solar mass of 3 kilometers, that in about 100,000th of a second, light will be at the other side. So 100,000th of a second, multiply that by a log, maybe multiply by 10 or 20 or so. That's still a 10,000th of a second, still a very short amount of time that the information comes out. And that is, and the claim is that's the most significant time scale for the black hole. Information cannot stay hidden longer than that. In that respect, it behaves like an atom which also has vibrations. Sometimes two energy levels of an atom can come very close, which means there's a longer time scale involved. There are many time scales involved with a black hole eventually because it may have very, very many energy levels. But in general, the evolution law seems to need only about so tiny fraction of a second for the information to reappear again.
Thank you.
So let's thanks once again for the wonderful talk and inspiring discussion. So let's give big hands to Professor Gerard Hooft. ต้องทำอะไรต่อไหม
จบบอกว่าใครไม่ได้ขนมก็มา
ถ้าใครยังไม่ได้ขนมนะคะอาจารย์บอกว่าให้ To every audience who joined this event, so we have 3D pictures card, 4 of them, right? Different. อะไรนะอ๋อไม่เป็นไรไม่เป็นไรอาจารย์ก็พี่เจ้าไม่บอกอ่ะบอกให้พาวินมาช่วยทรานสเลทไม่เป็นไรอาจารย์